Hello. Today I want to talk to you about RC circuits. An RC circuit is a simple circuit consisting of a resistor and a capacitor. You can see I've drawn one here on the left-hand side. I'm going to focus on the simplest kind of RC circuit at first, and then we'll move to more complicated ones. This is an RC series circuit, meaning there's only one loop. You can see the loop here. There's a battery. I happen to have a switch in here as well, the resistor and then the capacitor, and the ordering of those two elements doesn't matter. Actually, the ordering of the three elements, if you include the switch, doesn't matter whatsoever. You can swap them and put one after the other. It makes absolutely no difference for the behavior of this circuit. So I'm going to take a look at how this circuit behaves when the switch is first closed and then what happens after it's opened. And in order to do this, I'm going to use a couple of quick online simulations, and I'm going to avoid most of the mathematics. I'm going to save that for the next follow-up tutorial. In this one, I'm really just going to focus on the model and the physics of what's happening. I will invoke Ohm's law here, and I'll also, to describe what's happening in the resistor, or across the resistor. And I'll also use this equation right here, which relates the charge on a capacitor to the voltage across it, to kind of describe the buildup of charge on this capacitor. And you can see I've written these two equations again here, dropping the delta signs as we often do, just for simplicity's sake. So I'll use those, but that's about the extent of the mathematics that I'm going to invoke. I may also talk about Kirchhoff's loop rule a little bit in this context. But as I said, I'm going to save the calculus and the differential equation mathematics that comes along with this type of a circuit for a follow-up tutorial. Also super important to understand, but I think it's better to get the basics first. So to get us started, I've put together a couple of quick simulations that I've built online from FET. You've seen these before, and I've used them in class multiple times. So I've built I've built the following RC circuit, and I also have this simpler one right here. And I want to start off showing you how this one works, just to give you a feel for what's going on. This simulation is not completely accurate in the sense that it doesn't have any resistance built into it in this path here. So when I'm charging the capacitor, I'm doing it without any resistance. Here, let me show you what I'm talking about. So what I can do here is, with the circuit hooked up as it is, you can see I've got this light bulb kind of off to the right-hand side that's disconnected, and the capacitor is connected to the battery, but there's no voltage at the moment. I've got some variable power supply here, really. And I can change the capacitance by changing the size of the plates and the separation and all that. You can see the capacitance changing up here. Okay, so I'm going to go ahead and just kind of turn on the voltage, and you can see what happens. And the simulation does a nice job of modeling both the buildup of charge on the plates of the capacitor and the electric field arrows in between the plates. I like that. It also shows you the direction of the current flow in the wire here. Right, it's to the left, and that's a bit confusing. Let's try that again. Let's go down here. Okay, so let's raise it starting now, and you can see what's going on, right? You've got the current flowing with an arrow pointing to the left here and to the right here. So what you need to be aware of is that FET is showing you the direction of electron flow, not the more typical conventional current that we think of. So just be aware that in this simulation and the next one I'm going to show you, we're talking about electrons flowing. Now, I still consider this to be very unrealistic for a couple of reasons. The biggest one being that without any resistance in the wire, when you kind of turn on the voltage, you immediately charge the capacitor. It seems to get up to full charge immediately. There's no time involved. And the whole point of RC circuits is to focus on that transient period, or that time period when the charging is actually happening. And similarly, when it's actually discharging. There's a period of time that takes for that to happen, and that's a finite amount of time, and that's when the really interesting physics is happening. And this just completely glosses over that by giving you wires that have no resistance. And so it's quite unclear what's going on here. So while I like this simulation because it shows you the concept of the plates getting charged, and I love that electric field in there, I like the bar chart up here and all, I really don't like the concept that things change instantaneously in this little simulator, and that's bad because nothing actually behaves that way. In fact, you can watch the voltmeter on the right hand side at 0 volts, and it just mirrors instantly exactly what's happening at the battery as I raise the, see that? So now you watch when I get to 1.5 volts on the battery, the voltage across the capacitor is also 1.5 volts instantly. All right, unrealistic completely. Now if I switch these to the light bulb, then I take my charged capacitor and I discharge it through the light bulb. All right, and this is a little bit more effective because it actually takes a little bit of time for the discharge to happen, and you can see that. Watch. All right, and you can see the voltage going down on the capacitor as that time passes. So this is a little bit better. They got this part right. Let's watch again. So first I'm going to go over here and unrealistically and instantly charge my capacitor. Done. Okay, would never actually be that quick. And then I'm going to come over to here and discharge, and you can actually appreciate the discharge process taking that time. Watch again a couple things. Watch not only the light bulb start off bright and dim, but watch the electric field arrows dissipate in between the plates of the capacitor. Watch the charge diminish, and watch the voltage on the voltmeter, which starts at 1.5 volts across the capacitor. Watch it drop as time goes on, and it discharges. Okay, so that simulation is made to give you just a quick, well, to give you a feel for what's happening with these capacitors in circuits. But this is a much better one, and this is the one I actually put together. I built the circuit itself, and you can see over here is the capacitor. All right, and I've got some important numbers I'll point out. So the capacitance is 0.1 farads. I've got the resistor up here, which is 25 ohms. I've got the switch, which currently says infinity ohms because it's open, right? And then I've got the battery over here, 120 volts, and 5 ohms of internal resistance. I threw that in there just to keep it interesting. What that really means is that this circuit has a total resistance of 30 ohms. Okay, you just treat this 5 ohm resistance inside the battery as if it's an external resistor somewhere in the circuit. So I've got 120 volts. For my battery, I've got 30 ohms of total resistance in this series circuit, and then there's my capacitor. I've also got a graph to show the current as a function of time when I close the switch, and I also stuck a second ammeter here, just kind of a non-contact ammeter that hovers around the wire. Using these things, use magnetic field principles to measure the current in the wire. Such things do exist, and I've got that there just so you can see a nice reading of the current, because the graph is a little bit sketchy and you can't see exactly what's going on. All right, so now I'm going to close the switch at time 0, and I want you to watch what happens. Watch the current begin to flow. Again, this is electron current, so you're going to see it flow counterclockwise in this circuit. All right, here we go. All right, there goes the current. You can see the current is dropping as time goes on. And you can actually see that reflected in the graph, which is asymptotically approaching 0. A little annoying that it starts off in negative territory and goes to 0. But there you have it. All right, and as time goes on, eventually you can see the current is in fact, looks to be approaching 0. And my capacitor is now finally charged. And that took a certain amount of time. It does not happen instantly. And it's owing to the combination of the capacitance and the resistance in this circuit, that time that it takes to charge that capacitor. All right, if I open the switch again, nothing immediately happens. The capacitor stays charged. I have no means of discharging it in this particular example because I don't have another light bulb or something over here that I can connect to it. All right, I'm going to leave that off until a little bit later. So if I close the switch and open it and close it and open it and close it and open it, nothing happens. Now I can conveniently come over here and discharge it if I want to, and then I can reset and start again. So watch it one more time. Okay, again, watch the current. It's quite high at first, and then it decays to 0. And look at the actual value of that current initially. Okay, let's discharge. Okay, so again, I've got a 120 volt battery, and I've got 30 ohms of total resistance in the circuit. And when I close this switch, watch the value on this ammeter over here at the instant that I close it. Here we go. Watch. And you can see it's in the high 3s. It's actually 4. It's actually 4, as you would expect. Again, it's 120 volt potential difference of the battery. 30 ohms of resistance, 120 divided by 30 is 4 amps. But that 4 amps doesn't last for long, because as the capacitor starts to accumulate charge, it becomes more difficult for this battery to continue to pump more charge to the capacitor. You can think of it a lot like a parking lot that's getting filled up with cars. It's getting plugged up as time goes on. It takes longer, and it's more difficult to fit more cars in the parking lot as it fills up. Okay, but at least initially, at time 0, let's go ahead and discharge this thing. The current is initially 4 amps, which is what it would have been forever if I remove this capacitor, take it out of the circuit, and just connect these 2 wires and throw the switch. It's 4 amps continuously, forever and ever and ever. Okay, so what the capacitor really does is it introduces some time variation into this circuit. It says, yeah, you know, your current can be 4 amps, but just initially, and then we're going to drop asymptotically approaching 0. Now, there are mathematical functions that model this behavior, and they can be obtained by solving a differential equation that you write for the circuit, and we're going to do that in a follow-up tutorial, but we don't need to look at that just now. Okay? All right, now, if I could also pull out a voltmeter and take this, and we'll put this across the capacitor, right? And then I'll open the switch again, and this time discharge the capacitor. Here we go. Okay, so right now I have 0 volts across the capacitor, and I think, you know what I'll do while I'm at it, I'll take another voltmeter if I can. I may not be able to have 2 at once. Let's see. No, I can't. Okay, so watch, we'll do this in parts. So watch the voltage across the capacitor as time goes on. When I first close the switch, it's 0 volts now. It will be 0 volts for that instant after I close the switch. And then it starts to climb, it starts to climb, it starts to climb, right? And as we watch long enough, this is going to asymptotically approach 120 volts. Right, you can see that happening, which of course is the potential difference across the battery. Here we go. All right, now let's do the same thing. Let's again discharge the capacitor. Let's take this, let's put it across the resistor this time. Okay, all right, watch this. This will start off at 120 and drop asymptotically to 0. And in fact, at any instant in time that you were to look at this circuit, you would find that the sum of the voltage drop across the resistor and the voltage drop across the capacitor, the sum of them, would have to equal 120 always, at every instant in time. So when I first close the switch and the current is high, the resistor drops all the voltage. 120 volts across the resistor, 0 volts across the capacitor. As time goes on, the voltage across the resistor begins to die, begins to drop, and the voltage across the capacitor begins to rise. And the sum of those two is always equal to 120, because that's Kirchhoff's loop rule. Okay, again, that's assuming that there's no voltage drop anywhere else in the circuit. And actually, I realize I'm lying a bit because I forgot about the 5 ohm internal resistance inside the battery right there. So what I just said to you is true if in fact this is all the resistance in the circuit. So if I got rid of this here and I say change internal resistance and I drop this back down to 0, and then I take this and I take the resistance of the battery and I change it and I bring it back up to 30, now everything that I've just said is true. The voltage drop across this resistor is in fact 120 when this is 0, and then they flip-flop. Okay, but before, with that little bit of internal resistance inside the battery, there was a voltage drop inside the battery across that resistor. So this guy here was never really 120. Right? It was this resistor and the one inside the battery were dropping the 120 volts. So now this will be a bit more, I think you'll be able to see this voltage start off a little higher than you did before. Here, watch. Yeah, see? Okay, now with that information, what you can do is you can kind of come back here, look at the circuit, and using these formulas that you see here, you can calculate different quantities, like, for example, the final charge Q on the capacitor. or the initial current I in the resistor. Everything can be determined from what you see here. So if I steal the values that I have in the simulator over here, I think I had a 0.1 farad capacitor, and let's go with the 30 ohm resistor. That's all external to the battery. All right, so we'll label that in here so I don't forget. 0.1 farads and 120 volts. So if I ask some questions about this, like for example, at time 0, when right after the switch is closed, at t equals 0, which again implies that the switch has been connected, but at that instant, immediately right afterwards, what is the charge across the capacitor? Let's get some values. So what is Q? Okay, now I know at that instant of time that the voltage drop across the capacitor is in fact 0. So I know using this equation right here that the charge on the capacitor is in fact 0, which makes perfect sense because it hasn't any time to build up any charge yet, of course. What's the current in the resistor I at that point in time? Well, as I said before, at that moment in time, the voltage drop right here across the resistor is 120. Only for that instant. And therefore, with a 30 ohm resistor and 120 volts, I wind up with a 4 amp current initially, like so. All right, now let's take a look at it after a long time, which I guess the best way to do this actually is to say t approaching infinity. After a long time. There. Not so good. So what do we have? Well, you saw again, when running the simulation, that as t approaches infinity, the voltage drop across the capacitor approaches 120. Okay, so this becomes 120 now. And the capacitance again was 0.1. So 0.1 times 120, that's easy. That implies 12 coulombs of charge on that capacitor. And if I do the same thing for the resistor, you already know the answer, but at that point the voltage drop across the resistor is no longer 120, it's now 0. And so with the 0 volts across it, we wind up with a current of 0 from the equation delta V equals IR. Okay, and any other quantities that we wanted to calculate, like what is the power being dissipated in the resistor, P equals I squared R, right? Or also we can calculate it as IV. Any of these things we wanted to know, we could calculate that now at either of these points in time, at t equals 0, t equals infinity, because we know the current. If you wanted to know the energy stored inside the capacitor, U sub C equal to 1/2 CV squared, right? There's a couple of formulas for it, but this is one of them. You can get it now, obviously, because you know the voltage across the capacitor is initially 0, and at time approaching infinity, it's 120 volts. So you can do all other calculations that might matter to you. Okay, just knowing that. And that's basically how these things work. Now, to get into it just a little bit more, if I were to make a graph of voltage versus time, okay, we'll just do this quickly. So there's T, and here's the voltage across the different elements, and I'll use orange to represent the capacitor, and I'll use blue to represent the resistor. So this is going to go like this. Something like that. And here, this is 120. And this is the resistor, and the resistor is going to start there, and it's going to kind of die down like this, asymptotically approaching 0 as time goes on. All right, and as I mentioned before, if you take the value of this and the value of this at any point in time t, you'll find that they sum up to 120 always, and they have to because of Kirchhoff's loop rule. And then finally, if I were to make a graph of current versus time in this circuit, I versus t, that would, let's use pink for that, that would start off at 4, as we know, and it would decay. This is exponential decay, actually, and it would decay asymptotically to 0 as time goes on. And the simulation showed that, but it showed it in the negative area of the graph, rising, kind of coming up like that, okay? All right. Now, there's actually a time factor. It's called the time constant. It's usually labeled tau for these circuits. Tau. It's equal to R times C. This is the time constant for this circuit. And it ends up being literally that, the product of the resistance and the capacitance. And you can calculate it in this case because you know both of these things, right? It's 3 for our circuit. 3 seconds, in fact. And that's not arbitrary. That's based on an exponential decay graph. And I'll talk more about what it is and why it's defined that way when we do some of the mathematics of this. But basically what it's telling you is it's giving you a way to measure the decay of the current in the circuit or the increase in the charge across the capacitor as time goes on. And it's just kind of a characteristic time that's a way for us to describe the behavior of this circuit. Right? R times C, the time constant of this circuit. And again, I'll explain exactly what it is and mathematically why it's the product of R and C in a follow-up tutorial to this one. I think it's just important to put that out there now for the time being. Okay, that's all for this, and I'm going to wrap it up, and I'll come back with something a little bit more involved when we look at the discharging of this capacitor. Thanks for watching.